Okay. All right, so we finally have that all sorted out. Let's get started. Okay, so let's see. Today we are going to talk about quantifiers and proofs. Okay, so let me remind you where we were last time. Okay, so let's see. Can we maybe? Okay, so let me back up to where we were last time. Remember we talked about, we were trying to say, how do we make precise statements, right? Precise statements in math. And we defined what we called a proposition, which is a statement which is either true or false. Right, and then we said there are these connectives, like and, or, and then there was this very special one called implication, which we are going to be using all the time. Right, so P implies Q. And the truth table for P implies Q is right there. It's true except in one case. The only case in which it's false is if P is true and Q is false. Right, remember we said if P is false, then P implies Q is automatically true. Right, it's vacuously true because it has, that particular implication has no responsibility anymore once you know that P is true. And then we did this example which I flubbed because I transposed something. So let me go over it again, just so that it'll recall things for you, and then we'll also do it a little better this time. Okay, so we have this implication: if P is prime and larger than 2, sorry, if X is prime and larger than 2, then X must be odd. Right? So right here, P is this proposition, X is prime and larger than 2. Q is this proposition. And this time I hope you all see that if P is true, then Q is true. Right? Any prime which is larger than 2 must be an odd prime, must be odd. Okay, so now we can also look at the converse of this statement, which is if Q, then P. Right? So this says if X is odd, then it must be prime and larger than 2. That's clearly false. Right? You know about this proof by induction that all odd numbers are prime? No? Okay. Well, you should look it up. It's sort of this joke about how different people in different professions sort of view proofs in a different way, different levels of, rigor. Okay. Actually, talking about precision and different levels of rigor, right? There's a story about three people who were hiking in the Highlands in Scotland when they happened to spot a black sheep. So the first one, who was just a layperson, sort of exclaimed happily, do you see all the sheep in Scotland are black? And so his companion, who was a scientist, sort of said, look, surely you are overgeneralizing. Surely all we can say is that some of the sheep in Scotland are black. So the third person, who was a mathematician, sort of stayed quiet for a minute or so and then sort of hesitantly spoke up, and he said, surely all we can say is there's at least one sheep in Scotland that is black on one side. Okay, so back to this implications. So there's this other concept in implications, which is that of the contrapositive of an implication. And this is a very important concept. So if your implication is P implies Q, then the contrapositive is not Q implies not P. And unlike the converse, which may or may not be true, if P implies Q is true, then the contrapositive is always true. And if P implies Q is false, then the contrapositive is always false. So the two are completely equivalent to each other. Right? So in this case, for the statement that we had, the contrapositive is this. So we say, if not Q, if X is not all, then not P. Then it's not the case that X is both prime and larger than 2. Right? So you can restate that. You can say, if X is even, then either X is not prime or X is less than or equal to 2. Right? And you should make sure that you understand that is actually a correct statement. Right? That's a true statement because P implies Q was true. Yeah, somebody in the back?
If you just have two random true statements,
yeah.
then is the implication statement still true? Because they don't necessarily imply each other, but you still
yeah, so you know, this notion of implication is different from your daily notion of causality. Right? So it doesn't have to be that P has a causal effect on Q. You know, it doesn't have to be the case. So when we say P implies Q, we just mean this, right? It satisfies this truth table, right? So in our you know, when we use it in our usual everyday conversation, we wouldn't say that you know, the sky is blue, therefore this particular lecture started late, right? Even though both these statements happen to be true today, right? So the implication is true as far as a logical implication goes, although, well, okay, you know, it wasn't because the sky was blue. It wasn't because I was dawdling outside that we, you know, it was for other reasons, as you saw. It could have been, but it wasn't. Yeah. So everybody's happy with that, with our notion of implication? Okay. Okay. So okay. So now let's move on to talking about quantifiers. Okay. So often we'll want to make statements about every natural number or every integer or every person in the world, you know, things like that. So, or there exists an integer, right? And so we might have statements like this. So for example, we might say for every natural number n, it's the case that n squared plus n plus 41 is prime. Do you think this is a true statement? Do you know how close it comes to being true? So you can try n equal to, well, n equal to 0, it's true. N equal to 1, 43 is prime. N equal to 2, well, 4 plus 5, 47, it's prime. N equal to 3, 9 plus 1, 10, 51. Is it 51? I'm sorry, it's 53? Oh, sorry, it's 53. Yeah, right. Okay, 53, it's prime, right? N equal to 4. 16 plus 4 is 20, 61. It's prime, right? Is 61 prime? N equal to 5. 25 plus 5 is 30 plus 71. It's prime? It's prime. N equal to 6. 36 plus 6 is 42 plus 41 is 83. Prime? Yeah? Ridiculous, right? Okay, I assure you, you can keep going for a long time before you find that it's not true. Okay, so anybody can guess how to jump to a number where it's not true that it's prime? What value of n? Yeah? 41. 41, excellent, yeah. So if you look at 41 squared plus 41 plus 41, this is not prime. Is everyone convinced? Yeah, because it's 41 times 41 plus 1 plus 1, right? That's obviously not prime. Okay. Now, in terms of you know, in terms of typeface, let me just say, you know, those n's down there are also, it's also the set of natural numbers. By the way, the natural numbers are 0, 1, 2, 3, and so on. The integers are, minus infinity to plus infinity, right? Minus 0, they contain 0, minus 1, minus 2, etc., 1, 2, etc. And the positive integers exclude 0. So you have 1, 2, 3, 4, etc. Right? The negative integers are minus 1 down to all the way down to minus infinity. And 0 is neither positive nor negative. Okay, that's the usual convention, but, okay, so, all right, so now in terms of quantified statements, we'll also look at quantified statements like this. So for all natural numbers x, there exists a natural number y such that y is greater than x. Is that true or false? True, right? Because it says there's no largest natural number. Right? Okay, so let's see. Let's try to understand how quantifiers work. So remember these are actually from your homework, but let's go ahead and solve 2 of them. It'll get you started, and right. So I picked these out of a book called Symbolic Logic by Lewis Carroll, who you might know for other reasons, right? Right. Okay. So if he had not written Alice in Wonderland, he'd still have been, he wouldn't have been famous, but he'd have been known because of this book, right? Because this was one of the earliest books on symbolic logic. Okay, so Lewis Carroll being Lewis Carroll, he has a droll sense of humor, so these statements sort of reflect that. Okay, so you have these propositions: P of x is going to a party; h of x denotes x has failed to brush his or her hair; f of x looks fascinating; t of x is tidy. And now what we have to do is we have to write out these 2 statements in quantifier notation, right? So no one who is going to a party ever fails to brush his or her hair. So this is a bit confusing, right, when you first look at it. So you might want to sort of reparse it. You might want to say, well, how is this sentence actually put together? It sort of says, no one ever fails to brush his or her hair who is going to a party, right? Okay, so the way you would write it is for all x. So we have the universe U is the set of all people. So for all x in U, P of x implies h of x, right? So no one ever fails to brush his or her hair if he's going to a party. So if x is going to a party, then he doesn't fail to brush his or her hair. I'm sorry? So that's why it's for all x, right? For for everybody, if no one ever fails to brush his or her hair who is going to a party. If okay, so the way you would read it is no one ever fails to brush his or her hair if he is going to a party. So if somebody is going to a party, then they don't fail to brush their hair. Yes? Negation where? Sorry. Okay. So let's take it slowly. Sorry. Okay. So let's first try to understand what this statement actually is saying, right? So can we agree that what it's saying is everybody who goes to a party brushes their hair, right? Yes. Does anyone disagree with that? Yes. Oh, I see. Oh, sorry. My mistake here. So let's. Oh my God. Okay. 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 Are we all on the same page now? Sorry about that. Yeah, I made a typo. Okay? Yes.
You rewrite a statement using net.
I'm sorry?
Then you rewrite a statement using net existence.
Yeah, so now if we look at the contrapositive of this, um, um, so you could also say that this is the same thing as saying, oops, this is the same as saying, oh no, sorry, we seem to be, okay. So this is the same as saying for all x in U, not h of x implies not p of x, right? It's saying everybody who doesn't brush their hair, right? If somebody is not brushing their hair, they are not going to a party, right? They mean the same thing, right? Okay. The second one says no one looks fascinating if he or she is untidy. So it's you can write that as for every x in U, if he or she is untidy, so not t of x. So not you can write like this, or you can put t of x bar. I don't know which convention I'm not terribly worried which one you say. If he or she is untidy, he or she does not look fascinating. So not f of x, right? Which again, if you want to take the contrapositive, says for every x in U, if x looks fascinating, then it must necessarily be the case that x is tidy. Okay? Yes.
So can we use negation of the exponential multiplier?
I'm sorry?
Can we use the negation of the exponential?
Okay, so we could also write, you could also see if you could write it in terms of existential quantifiers, because for all x is the same as not, there exists x not, right? So let's see. Are we doing that in the next slide, or maybe? Okay, so we're very negating. Okay, so let's do a negation here, right? So if we say for all x in U, p of x implies h of x. Okay, this is the same thing as saying if it's true for every x that this is true, then it's not the case that there exists x belonging to U such that this statement is not true. Right? These have the same meaning. If it's the case that for every x, p of x is true, then that's the same thing as saying there does not exist a counterexample. There does not exist x such that p of x is false. Does everyone get that? Okay, so let's write it out. For all x, p of x implies h of x is the same thing as saying not there exists x such that not p of x implies h of x. Okay, now how do you say not p of x implies h of x? Is there a simpler way of saying that? So if p of x implies h of x is false, then what must be the case? What's the only way this can be false? Yeah. So it has to be the case that p of x and not h of x. so not h of x, right? Right? It's got to be the case that, let me write this a little more clearly. It's got to be the case that not p of x and h of x. All right. Okay, so yes.
Can we turn more on the last slide? Why is not PRX?
Okay, so I'm claiming that if you negate this, if you look at naught of this implication, right? When is that true? So when is p of x implies h of x true? It's true if p of x is false or h of x is true. Right? Whenever h of x is true, the implication is automatically true. Whenever p of x is false, the implication is automatically true. It's vacuously true. So when is it false? There's only one out of the 4 cases where it's false. The only way it's false is if p of x is true. Oops. Sorry, did I make a mistake again? Okay, so sorry. Okay, so let's try again. So the only case in which it's false is if p of x is true and h of x is false. Okay. Sorry, I just don't have enough room to write this. I'm just going to write this down here. If p of x is true and not h of x. Okay. All right. So now let's try to look at other things that you can express using quantifiers. Okay, this will give you an intuitive understanding of what quantifiers are. So how many of you have played this game of matching pennies? Nobody? Okay. Sorry, can we settle down here? Okay. So matching pennies is a game that two players can play, where each of you has a penny, and you hold it. You sort of hold it out. Either you show it. Usually, you show it simultaneously, and you either if both are heads, then I win, and if both of them match, then the first player wins, and if they don't match, the other player wins. Okay, so you have 2 players. You call one of them player 1, the other 2 player 2, and the first player wants the 2 coins to match. The second one wants them to not match, and they simultaneously reveal the coins. If they are both heads or tails, the first player wins. If they are both, if they are opposite, then the second player wins. So now we can say there's we can write a proposition p of xy, which says, or let's call it instead w of xy, which says the first player wins, which means that x equal to y. Right? They match. Okay. So now you could write a statement which says that the first player has a winning strategy. And the way you would say that is there exists something that the first player can do such that no matter what the second player does, the first player always wins. So the way you'd say that is there exists x such that no matter what y, the second player, this is the first player, that's the second player. So there exists an x such that no matter what the second player plays, the first player wins. Okay? What's the negation of that? So let's try it. So we'd say not there exists x such that for all y, w of xy. And our rule is that if you want to negate a quantifier, you sort of flip it, and then you flip whatever is inside. the quantifier. So this is the same as saying, okay, so when you negate the exists, you get for all x not whatever is inside. Okay? So now again, we have a not for all. How do you negate a for all quantifier? You flip it, yeah, make it a there exists. So you'd get, this is the same as for all x, there exists y not w of xy. Okay, not w of xy, so meaning that the first player does not win, right? In this game, it's a two-player game where either the first player wins or the second player wins. There's no third possibility. So this is the same as saying the second player wins. Okay? Okay, so what's this statement telling us? It's telling us that the second player has a winning strategy because it says no matter what the first player does, no matter what the first player plays, there's something that the second player can do. There's a move that the second player that the second player can make, which wins the game. Okay. So now, which one do you think has the winning strategy in this matching pennies game?
Well, I just want to ask, what universe are you like quantifying it?
Yeah. Okay. So I'm keeping that. Yeah, I was leaving that implicit. So what x they exist? You know, all this is in the universe heads, tails. Right? So these are coins, so they have two possibilities, heads and tails. That's what we are always quantifying over. That's what the moves belong to. Okay? So what do you think? If you were being asked to play this matching pennies game, and instead of playing simultaneously, you had these different rules where first one player goes and then the second player goes. Which one would you want to be? Second player, obviously, right? Because you can determine the outcome. And so in this case, this is true. Right? So the second player always has a winning strategy. This is always false. This is false, right? The first player does not have a winning strategy. Right? Now, as you can see, there's a theorem in here. Right? We proved something. We proved, you know, this is how you can write any old game. So if you have a game like chess, right, where you alternate moves, you can say, is it true that white always has a winning strategy in chess? You could write out a formula like this for chess. You could say, for chess, you could say, is it true that does there exist a move for the first player such that for every move for the second player, there exists a move? Okay, sorry, maybe I'll write it this way just to make it clearer. So I'll write y for the moves of the second player. So does there exist, is it true that that there exists a move for the first player such that for all moves that the second player can make, there exists a move for the first player, right? So this was the first player's first move, second player's first move, first player's second move, second player's second move, etc. You can keep quantifying, you can keep going such that it's a win for, you know, x1, y1, so on, xn, yn. You know, if you look at the board position, then W sort of says it's a winning position for white. Right? So this is a statement if you suitably make up this predicate W, which says if you make the moves x1, y1, x2, y2, etc., then it's the case that white won. You know, the first player won this game. So if you write out such a statement, then this would say white always has a winning strategy in chess. What would the negation of this be? So you could also negate this. And if you negate this, you'd put a negation up front. And now remember, by these rules, we could just push the negation all the way through. And what would we get? We'd get for all x1, there exists y1, such that for all x2, there exists y2, etc., such that not w of x1, y1, etc. So now, okay, in chess, you can either win, either the first player wins or the second player wins, or it's a drawn game. But let's pretend for the moment that chess was a kind of game where either white wins or black wins, and there's no possibility of a draw. Then what this would be saying is, in such a game, either the first player has a winning strategy, right? If God were playing for the first player, he'd always win, right? Or it's the case that the second player has a winning strategy, right? The strategy might be very, very hard to find, but it's always the case for such a two-person game where at the end of the day, one of the two players wins, that either the first player has a winning strategy or the second player has a winning strategy, right? And we sort of derived all that from this very simple rule about how we take existential and universal quantifiers and we negate them. Does it make sense? Okay. Now, let's see. How far are we into the lecture? What time is it? 4:24. Oh my God. Okay. So, well, anyway, okay. So we are going a bit slow, but that never mind. Surely at this point you need a 2-minute break, right? So, yes, no? Let's take a 2-minute break. All right? Okay, so these are accounts.
I was just going to ask you.
Yeah, do you want to pass them around?
Sure, yeah. Can I do it right now? Or?
Sure, you can do it right now. Okay, so can you pay attention for a moment?
Sorry, guys. For the homework submission, we're doing electronic homework submission, so you need an account form. You're not going to need to code anything, but you're going to need an account form so you can use GLOOKUP like you used to submit things and then check your grades. This way, hopefully, you can get faster feedback on your grades. It should be a lot easier on the readers to not have to shuffle papers around and come back to you as quick as possible. I know there's some questions on Piazza. Some of you don't have scanners and stuff. That's totally fine. I don't either. There are some on campus. Preferably, you lock-back everything. If you don't, you can make things pretty clear still using Word or Google Docs because there's an insert equation function, and the same way in LaTeX they type backslash and like sigma or whatever, and it'll make those shapes and whatnot. You can do all of that in either those and then yeah, ideally you would use LaTeX. So anyway, whatever is most legible, the point is to get your homework there.
Did you do anything extra of it?
Yeah, you can make the pictures later now. Convert it to a PDF. Everything should be a PDF. That way it's consistent to the readers. But yeah. If you have a good camera on it, I think it's all right. Whatever works so you can see it. This is just going to be a lot more convenient for the readers so that they can get you feedback on your homework faster. So that they basically identify how you're doing it in class.
Sorry, and should we ask at the end of the class? How long do you think this will take? Maybe a while, right? Yeah, okay.
Okay, I'm going to pass these out at the end, guys. So do not leave without one of these, right? You cannot submit your homework without a form. So, yeah, I'm going to set it down and you guys pass it around in a second.
Yeah.
Okay, so make sure you get one of these. If you don't get one, check it with me at the end of class and we'll call it.
Okay. Okay, so let's get started. Okay, so just a couple of warnings about quantifiers. Be careful with them, right? If you think about them carefully, common sense will get you the right answers, but do think about them carefully. So for example, quantifiers do not commute. So you cannot interchange quantifiers freely. For example, if you have a statement like for all x, for all natural numbers x, there exists y such that y equal to 2x. Is that true? For every x, for every natural number x, there's another one which is twice as large. Yes. Now if you interchange these two quantifiers, right? So if you interchange, if you swap the two quantifiers, then you get a statement which says something completely different. It says there exists y such that for all x, y equal to 2x. Is that true? No, right? Because this is saying there's a particular y. So for example, it might be y equal to 100, but you're fixing that y, and now you're saying for every x. So now the rest of the statement says for all x, 100 equal to 2x. But that's obviously false, right? Okay, good. So that's the first thing. The second thing to be careful about is how quantifiers work. Again, so suppose you have oh, okay, sorry. Okay, so let's get rid of this for the moment. What did I want to say? So suppose you knew something like this. For all x, there exists y, p of xy. And suppose you also knew for all x, there exists y, q of xy. Okay? Surely you should be able to say, for all x, there exists y, p of xy, and q of xy. Does that look right to everybody? Right? Because if p of xy is true and q of xy is true, surely p of xy and q of xy is true, right? Does it look right to anybody? Yeah? Does it look sort of okay to people? It looks sort of okay, right? Okay. To how many people does it look really wrong? Oh, good. Okay. So let me say, okay, again, this is something where you have to be careful with quantifiers. So what's it telling us, right? So first of all, this is saying for every x, something is true. So what's true? So let's try to give it a meaning so you can picture it. So for example, let's say p of xy is says it's a proposition which says y equal to x plus 1. And suppose q of xy is true whenever y equal to x minus 1. Okay? So now, is this statement true? Is the first statement true? Is it true that for every x, there exists y such that y equal to x plus 1? Assume that, assume that we are working over the integers. Yes? Yeah, so this is correct. How about, is it true for every x that there is a y such that y equal to x minus 1? It's true, right? Okay, so what about this? Is it true that for every x there exists a y such that y is equal to x plus 1 and y equal to x minus 1? No, right? Because now we are saying it's the same y in both cases. So it's not true. Right? So you have to think through. You have, be sure that you can picture what's going on. Right? Okay. All right, so now we are going to move on to talking about proofs. Okay, and so proofs are, we're going to be obsessed with proofs for the next 2 or 3 lectures. With what they are, how you write them, how to be precise, all that sort of thing. Okay, so what's a proof? Well, a proof is, it's the ultimate guarantee that something is true. Right? There are many things, there are many notions of something being true. You can say it's true that the sun always rises in the east. Why is it? Because it's out of experience. Right? But then there's a different level at which one says something is true when you have proved it. Right? Okay. So what does it mean? What does it mean that you prove a certain statement? Well, to prove a certain statement, what you do is you first start with some axioms. Right? These are statements you assume are true. So what are examples of axioms? For example, examples of axioms might be the parallel postulate in geometry, right? Which says that if you have a line and you have a point not on the line, then there's one and only one line that goes through it. Now, it's an axiom because it describes a certain kind of reality. For example, planar geometry. But in other kinds of geometry, it's not true. So you can change the axiom and you get some other system, right? So if you take into account the fact that the Earth is curved, then you have a different axiom. You might have that there are more than one lines parallel to a given line through a given point, or that there are no lines, right? These are different kinds of geometries. So we first fix the system that we are in by fixing the axioms. Then we have these rules of inference. Rules of inference are things like we've already said, like if you know P is true and Q is true, then P and Q is also true. Or if you know P implies Q and Q implies R, then also P implies R. Right? This is one of the most famous famous inference rules. Another inference rule, that's quite famous is if you know P implies Q and you know P, then you also know Q. Okay, so I'm sure many of you've seen this in this sort of famous sort of quotation where it says P implies Q, all men are mortal, Socrates is a man, therefore Socrates is mortal. Right? It's of this form. P implies Q, P, therefore Q. Or another implication rule is if P, then P or Q. Now, so what's a proof? A proof is a sequence of statements where each statement is either an axiom or that statement follows from the previous statements by one of these simple rules of inference. Okay? It's a proof because you don't have to use any ingenuity at all to test it, to check that it's true. Right? So coming up with the proof is difficult, but once it comes to checking it, you can just do it mechanically. In fact, to check a proof, all you need is a computer. So in principle, you've proved something if you can write it out in full detail and then feed it into a computer. And there's a proof checker which sort of goes through your claims and says, yes, okay, everything is correct. Right? So there's a completely mechanical, completely well-specified algorithmic procedure which says, here's how we check that the proof is true. Okay? So in this sense, proofs have everything to do with computers. Right? Even their definition has to do with computers. I'm sure you recognize something like this. Way back in high school or grade school or something, when you did geometry, you had to write down proofs in this horrible format where you gave statements and reasons and steps and so on. Okay, this is how. Okay, this is what proofs look like if you write them out in full detail. Or not even in full detail. This is not yet in full detail, but this is sort of heading in that direction. Okay. And so this is our notion. Formally, a proof is a machine-checkable sequence of inferences. Okay? In practice, this is way too cumbersome. In fact, it's even too cumbersome to do it in this planar geometry, in Euclidean geometry kind of proofs, which you may have learned in school. Even that's too cumbersome. So what we do in practice, what mathematicians do, is they skip steps. But then there's this question, how many steps do you skip? And the answer is it's a negotiation between you and your audience. It depends upon who your audience is and how skilled you are. So the more skilled you are, the more steps you can skip, because your audience knows that you can back it up, right? The more skilled your audience is, the more steps you can skip because you know they can fill in the details that you left out. Okay, so what does this mean for this course? What it means is that for the first couple of weeks, we are going to do as many steps as possible, as many steps as we can bear to do. And then as you get more and more skilled, you're going to start skipping steps and you're going to say things more and more intuitively. Because eventually we want to acknowledge the fact that every proof, every non-trivial proof must have an idea in it. And we want to focus on the ideas, not on these, not on this. So if you want to draw an analogy, a proof written in complete detail is like writing a program in machine language. You can do it if you really want to, but nobody really wants to do it. Right? So gradually you build up. You build up from machine language to assembly language to, and then soon we are going to be moving up to a higher level language where we trust each other and we can sort of do proofs in a more civilized way. Okay, so a few weeks into the course, we are going to get much more civilized and not do this sort of stuff. Okay, so I said before that proofs are intimately tied to computer science. In fact, I cannot stress enough how intimately it's tied to computer science. So early in the 20th century, logicians were trying to formalize what it meant to prove something. And the reason that they were trying to formalize it is because, well, it's the reason you do anything. It's because there was a catastrophe. There were problems in logic, and they didn't, there were these big monsters that sort of people showed existed in logic, and so they wanted to rule them out. And so how do you rule them out? How do you make sure that mathematics is consistent? And so they had to formalize what a proof meant. And to formalize it, they really had to formalize what a computation meant, because a proof, after all, is something that you can check using a computer. But they didn't have a computer at that point. So how could they formalize what a proof meant? Well, to formalize it, they really had to come up with this notion of computation. So computer science, in some sense, was born out of logic. Right? So the early logicians in the first part of the 20th century were laying the foundations of computer science. How many of you have heard of Alan Turing? Right? He was a great computer scientist, but he was also a logician. So he was sort of the first computer scientist we know. Okay? All right, so one more example of this. How many of you have heard of the P versus NP problem? Okay, so this is considered one of the greatest open problems in mathematics. Okay, and it's a problem about the nature of proofs, but it's also one of the greatest open problems in theoretical computer science. Right? So the Clay Foundation, the Clay Institute, which has put up this sequence of I don't know how many questions it was. Maybe it was 8, but now there are only 6 remaining. These were the most famous open problems in mathematics. And one of the most prominent one of those is P versus NP. So anybody who solves any of these problems gets a $1 million prize, from the Clay Institute. Okay. Okay, so let me say one more thing about proofs. So here's an excerpt from a book. I've taken this from the New York Times. It's from this book, Zero, the Biography of a Dangerous Idea. So it talks about this. It talks about a certain mathematician, Hippasus of Metapontum. So he was on a ship. He was stood on the deck preparing to die. Around him stood the members of a cult. So this cult was a secret brotherhood. This is in Greece, ancient Greece. Hippasus revealed a secret that was deadly to the Greek way of thinking, a secret that threatened to undermine the entire philosophy that the brotherhood had struggled to build. For revealing that secret, the great Pythagoras himself was sentenced. Hippasus to death by drowning. So to protect their number philosophy, the cult would kill. Okay, so the legend has it, or the story is that Hippasus was actually thrown off the ship. He was drowned because he revealed a certain secret. So what was the secret? Okay, so this is another paragraph from the book. This is the story of this is from the New York Times. It talks about this is a story of a revolution. You have normal mathematics, call it the Pythagorean paradigm. So this is this is the Greek mathematics at that time, the Pythagorean society, which was this cult. There's an anomaly, an inability to find a rational fraction that measures the diagonal of a unit square. This is followed by a mathematical proof that shows conclusively that there can be no such fraction. The Pythagoreans take an oath to keep this proof a state secret because it undermines the claim that all is whole number. So this was, this is the nature of state secrets back in the time of the ancient Greeks. Wasn't that a wonderful, innocent time? But Hippasus breaks the oath and reveals the secret to the hoi polloi, to the common man. As a punishment or as an act of vengeance, he is drowned. A revolution follows, and there's a paradigm shift to a new paradigm which allows for irrational numbers. So anyone know what this is talking about? Yeah, this is talking about the proof that square root 2 is irrational. Right? So this was, governments have been brought down just because of a proof. Okay, so that's the theorem. So we'll see how to prove this theorem if we have time today. Okay, so now in the second notes, in the second set of lecture notes, these are about proof, types of proofs, proof strategies. Now the particular proofs that we've chosen in those notes, these are not so important. We've chosen proofs that are as clean as possible, as simple as possible, so that we don't need any prerequisites for them, or as historically interesting as possible. What's more important there is that you should understand what these different proof strategies are, so that when we actually do them, when you actually have to prove something, you have all these available strategies to try. Or when you actually see a proof, you can follow the abstract structure of it. Okay, so the most direct, the most simple way that you can prove something is what's called a direct proof. You just do a sequence of implications. So you want to prove P implies Q, so what you do is you do it like this. You assume P, and then you show P implies Q1, Q1 implies Q2, etc., etc. Qj implies Q, and now you chain all these together, and so you say, P and P implies Q1, these two mean that Q1 must be true, and then you just go down the chain, and you say all this implies Q. Okay, so let's see a proof of this kind. It says for every x is odd implies x plus 1 is even. X is odd means that that there exists k. So okay. X is odd is the same thing as saying there exists k such that x is equal to 2k plus 1. Right? Actually, since we are doing a proof, since I'm doing a direct proof, I'll just do that. This implies that x plus 1 equal to 2k plus 1. Sorry, 2k plus 2. Which is of the form 2 times k prime, which implies that x plus 1 is even. Right? So you can see it's direct proof is what you'd expect. You just directly follow these simple implications along. Okay. Now there's another kind of proof which is actually surprisingly powerful. This is called proof by contraposition, right? So in proof by contraposition, you're trying to prove that P implies Q. But it's hard to prove that P implies Q. So you try, and it turns out to be difficult to do. So then you remember that P implies Q is the same thing as not Q implies not P. Right? So P implies Q is the same thing as not Q implies not P. So instead of proving that P implies Q, what you do is prove that not Q implies not P. And then once you're done with that, you conclude that P implies Q. Okay? Now at first sight, if you've never seen a proof by contraposition, you might think this is crazy, right? Because P implies Q is the same thing as not Q implies not P. How could it possibly be any simpler? Right? But this is the strange thing about proofs. Good proofs are like magic tricks, right? You sort of there's sort of this there's an element of surprise to them. You look at them and suddenly something is true and you've proved it and you don't quite know how it happened, right? So let's look at simple examples of this. Okay, so by the way, when I have that kind of an arrow, I'm using that to say implies, just because it's simple for me to do that when I'm typing in PowerPoint. Okay, so here's a theorem: if n and d are positive integers, d divides n. Then, if n is odd, then d must be odd. Okay, so if d divides n, n is odd, then d must be odd. Okay. Seems like a pretty simple, clear fact. It must be true. So let's try to do a direct proof. Let's assume. So if we try a direct proof, we'll start by assuming n is odd, which means that there exists k such that n equal to 2k plus 1.
Professor,
Yes.
quick question. What does it mean that d divides n? Does that mean that n goes through to n?
Oh, so here's what I mean. So for example, 7 divides 21. So to say that d divides n means that if and only if there exists some integer, these are positive integers, there exists e such that d times e equal to n. Right? Okay, so okay, and you'll notice I'm already being a bit sloppy here because I'm not I'm not saying there exists k which is a positive integer, right? So I'm sort of trying to go fast or trying to sketch the main points. But of course, you have to remember that at least for these couple of weeks, you're trying to be as precise as possible and not skip steps. Okay, so so you have to you have to bear with me. It's hard for me to not skip steps after all these years, but hopefully you won't have any such problems right now. Okay, so here's where we are. We are trying to show that if n is odd, d must be odd, right? So we know we are saying 21 is odd, 7 is a factor of 21. It must be odd, right? How can we possibly proceed? So we've started with assuming n is odd, and we know also that we also know d divides n. So this implies there exists e such that d times e equal to n. But now, how can we possibly combine these to conclude that d must be odd? Seems a bit difficult to do, right? We are sort of stuck. Okay, so now let's see what happens if we take the contrapositive, right? Suddenly things become so much easier. We don't have a barrier to go through. So let's try the contrapositive. So what's the contrapositive of this? If n is not odd, if d is not odd, then n is not odd, right? So if d is even, then n must be even, right? So does everyone see that this is much easier to prove? Right? Because what does it mean? D is even. This implies there exists k such that d equal to 2k. Right? And now you have the fact that d divides n, which implies n equal to d times e for some e. Right? Now you substitute, and so you get n equal to 2k times e. Right? So n is even. right? So you see how strange it is, right? You take the contrapositive, which is completely equivalent to the original statement, and suddenly you have no barriers to proving it. You know, it just goes through. It's the simplest thing. Right? Okay, so how should you think about this? I mean, you know, this is just the laws of thought. You know, this is how, you know, if you were how do you say this? If you were Platonist, if you were a believer in Plato's philosophy of reality, Platonic reality, right? Then you would sort of say, this is the nature of truth, right? That mathematics establishes the truth, but it has its own topology. It has its own, there are its own paths through which you can move easily. And you try to move in certain ways, then there are barriers there. But there are certain other paths which are much simpler to move down. And in this particular case, when you take the contrapositive, you find one of these shortcuts. You know, it's a path that's much simpler to go down. Whereas if you tried proving the original statement, you were going down a path that was difficult and long and so on. Okay, so that's what we're trying to learn here. Is not just these rules, not just how to put together these proofs, but also what lies behind them. You know, how ideas are chained together, and what their structure is. Okay, let's do one more, another type of proof which is also extremely powerful. It's a proof by contradiction. So the way it works is, if you're trying to prove the proposition P, what you start by doing is assuming not P. And then you have a series of implications, and somewhere along the line you prove R. Something R, which is unrelated to what you were trying to prove. And then sometime later you prove not R. And now you say there's a contradiction. Because you cannot have both R and not R follow from not P. And therefore, it must be the case that not P was false, and therefore P is true. Okay, so let me try to show you why this follows. So can anybody tell me why this follows? So why does this imply that P must be true? Can anybody tell me the structure of this argument? Yes. Sure, but why is not P true? So can you sort of show me why this proof by contradiction actually implies that not P must be false? Yeah. Okay, so maybe this is a bit tricky. So let me, I had something in mind. Let me just say what I meant. So you see, this proof, the way it's going as a direct proof, what it's saying is not P implies both R and not R. Okay? What do you know about R and not R? It's always false, right? This is a contradiction. So this is always false. So what we've shown is that not P implies false, that this implication is true. Now, in order for this implication to be true, what must be the case? The only way that this implication can be true is if not P is false. So it must be the case that not P is false. Right? Which means that P is true. Right? So everyone clear? So what we're using in this is we are using the fact that when you have this vacuous, sorry, not vacuous. When you have a contradiction, you're proving something implies false, and then the only way this can be true is if the antecedent is true. Okay.